So thanks for the introduction. As Heiner said, I am now freshly an assistant professor at University of Sherbrooke. That's in Eastern Canada. But I am also still an associate researcher at GEOPS, which is now Géosciences Paris-Saclay instead of Paris-Sud, but it's more or less the same university with a different name. And so I cannot see the chat now. So if you have questions during the talk, I guess you can just interrupt me with the sound, because I don't see the chat right now. Feel free to ask questions. And so today we're gonna travel a little bit in both space and time. So we're gonna travel to Eastern Siberia, and we're gonna talk about lakes there. Currently, how are they acting currently, and how they might have acted in the past, like several thousands of years ago. Let me check here. So this is going to be a three-part or a three-section talk. First, I'm going to just introduce you to the fascinating world of permafrost or frozen ground. That's going to be kind of a crash course about this, because it's less often talked about. And then I'm going to present some results from greenhouse gas emissions in different seasons in lakes in Eastern Siberia. And then third part of the talk, this is going to be about going back in the past and see how one of these lakes have acted during the last few thousands of years. So just a quick note here, it's the project, the MOPGA project called PEGS, or Permafrost and Greenhouse Gas Dynamics in Siberia. So it's based in France with colleagues from Paris-Saclay and LSCE, so basically in the southern Paris region. And this involves collaborations with other colleagues from France and Germany, and also Canada and Russia. So it's really an international initiative here. So if I start by asking you, what do you see in this picture, which is a pretty typical picture of Central Yakutia, and I ask you what do you see in there, I guess you would probably start by mentioning the forest. Like, this is the never-ending boreal forest, taiga. Lots of lakes. Maybe you will mention the river and this little village here that we can see in the background. And an amazingly flat landscape or topography, like the total absence of any mountain or any topographical feature. But what you would not see in this picture is actually the most important landscape feature in the region that has been there for tens of thousands of years. It's the permafrost, or the frozen ground. So we define that as a very simple way, as any rock or any soil with a temperature at or below 0 degrees Celsius for at least 2 consecutive years. So you can see an example here from Central Yakutia, and usually this kind of permafrost can contain 2 basic things, which are frozen ground, like any sand or clay or gravel or rock, but usually it's more or less soil, frozen soil, that can contain ice between the particles, between the grains, can contain organic matter as well. And you can also see these abundant, massive ice features that will be like vertical ice veins, or sometimes horizontal ice lenses or layers. And so this is pretty typical of the landscape there. And a last note here for this slide about what we call the active layer. This is going to be important in a few slides. We call the active layer the top layer that will thaw for each summer, and then that will freeze back each winter. So it's it's kind of the breathing layer on top of permafrost, which thaws every summer but freezes back every winter. This is the active layer. So where do we find permafrost? Actually, we find that pretty much everywhere in the northern hemisphere, north of 50-ish or 60-ish degrees of latitude. So it's a huge area. It's more than 20 million square kilometers in the northern hemisphere. So the more we get near the North Pole, the more we will have what we call continuous permafrost, or the deep, or the deep purple that you can see there, the dark purple, which is pretty much permafrost everywhere, 90% and more of the total landscape. And sorry, so more than half of the total permafrost area in the northern hemisphere is basically located in Russia. And the PEGS project that I was talking about is focused on permafrost dynamics and lakes and greenhouse gas emissions in a particular watershed, in a small watershed near the city of Yakutsk. So why is it important to study those frozen landscapes that are at the other side of the world? First reason, it's important locally because there are villages and cities that are basically that have their infrastructure built on frozen ground, and with climate change, you can have different impacts of degrading permafrost, and so degrading infrastructure, and so the stability of these infrastructures, roads, railways, buildings, and so on, are highly depend on the stability of permafrost. So it's important locally for the communities, but it's also important globally, because as we will see, permafrost can contain stocks of organic matter that will be transformed into greenhouse gases, and so it has importance for the global climate. So before we go any further, we will fix a very common mistake or error that you will see pretty much everywhere in the written or audio media. Permafrost does not melt. Permafrost will thaw because it's a soil, basically. So the ground ice melts, but the permafrost will thaw. It's like with Christmas dinners that are coming soon. I would make an analogy with the frozen chicken or turkey that you get out of the freezer. You will not have a puddle of chicken. You will have a puddle of water because there was some ice there that melted, but actually the thing, or the chicken or the soil, will thaw. Anyways, that was my little side note here. And so permafrost is currently evolving in the context of what we call the Arctic amplification. So you see here this map showing the observations from the last decades, mentioning or showing that the Arctic region has warmed faster and twice or three times as much as anywhere else on the planet, 3 to 4 degrees Celsius for the last decades. And this is a trend that will likely continue for the next century. You can see here the projections on the bottom map, and we see that the high latitudes beyond 60 degrees northern latitudes will be the regions that will be the most affected by Arctic amplification, of course, Arctic climate change. And so if we are talking about temperature increasing in the air, consequences temperature increasing in the ground. So this map here shows the thickening of the active layer, the active layer I was talking about a few slides ago. So for the end of the next century, models are predicting that this layer that thaws every summer will get thicker and thicker and thicker with time. And so this is something that is a direct consequence of Arctic climate warming, Arctic amplification. And this is something that is integrated in the models, a gradual and widespread thawing of the ground. But actually what we observe on the field is a bit different. It's not widespread, it's more localized in space, and it's also much more abrupt rather than gradual. So the models are integrated one type of phenomena, and actually in the field we observe different things like these spectacular craters that you can observe in Western Siberia, or those numerous thaw slumps that will affect the landscape. So these phenomena can really disturb the hydrology, the ecology, the geomorphology, and really a suite of phenomenon that will be affected in really a super fast way, I could say, yeah. So meanwhile, in permafrost regions, we have very abundant, extremely abundant lakes, aquatic ecosystems. Here, this figure shows the total lake surface area on the x-axis as a function of latitude on the y-axis. And we can see that most of the lakes on a global scale are located in, for example, somewhere between 50 and 70 degrees north in latitude. So basically, more or less in permafrost regions. So in there, lots of lakes, very diverse, different types, different forms, different depths, super abundant. So they play a key role on the landscape dynamics here, these freshwater ecosystems. And also they are not only abundant, they can also play a key role in global biogeochemical cycles, including the carbon cycle. Why is that? Because, for example, this map here shows the soil organic carbon stocks that are in the first meters of the soil. The black dots are actually field work or field samples, actual observations. And we can see that in the northern regions, there are some spots, for example, Hudson Bay lowlands or Western Siberia, where you have lots of carbon that is now currently frozen. So it's stuck there, it's frozen in the soil. But with warming that could be accelerated, this organic carbon can be released in the environment, can be eaten by microbes. And so this can produce lots of greenhouse gases like CO2 and methane. And you have an example here of methane bubbles that are frozen in an ice cover just on top of a lake in Alaska. And actually, I hope it's gonna work. So you should see a video right now on one of those lakes in Alaska. And we are actually seeing through the ice cover. And we see all those little bubbles that are different sizes and shapes that are frozen within the ice cover. And when we arrive at the bottom of this ice cover, like we can see now underneath this ice cover, we can see those bubble pancake shaped big methane bubbles that were formed at the end of the winter time and that were stuck beneath the ice cover. So of course, during the springtime, all these bubbles are going to be released in the atmosphere. So this is the same shot here, the same video, but the camera is filming upwards instead of horizontally. And what I want to draw your attention to here is these, again, we see the bubbles through the ice cover, and you can see the light is not scattered that much through the ice, but through the water. This yellowish brownish color is the sign that the waters are have high content of dissolved organic matter, dissolved organic carbon that will scatter and absorb the light there. And so this was for the natural ecosystems, but something that we sometimes forget in the natural science community is that lots of people are actually living in the Arctic nearly 5 million people in different, in cities, small cities, villages, and sometimes bigger cities like Yakutsk in eastern Siberia with 300,000 people, which is the world's largest city entirely built on permafrost. And there are also various indigenous peoples there that have been living there for centuries, sometimes millennia. And I will mention today the Yakut people, or the Sakha people, as they call themselves, in eastern Siberia, indigenous people that have been living there for since the 12th or 13th century, so quite a long time now. Yeah, is it working? Yeah. So this map here will show where the infrastructure might be in danger for the middle of the 21st century, which is kind of soon in 2050. The areas in red show where permafrost thawing could mean severe damage to the infrastructure by the middle of this century. For example, the northernmost railway, the Obskaya Bavanenkovo in the Yamal Peninsula, could be in severe damage before the middle of this century. And actually, some impacts are already visible. You have an example here in the city of Yakutsk last June. So ground subsidence or collapse that was formed by the thawing of ice-rich permafrost. So really direct impacts for northern communities. Here's an example here. So this is a drone shot showing very old and ice-rich permafrost that has been thawing very rapidly near a water pipeline that you can see here. So when some ice melts, it releases water, and this water will generate some heat or some energy, and this will result in what we call thermal erosion. So you don't only have mechanical erosion of the soil, you also have thermal erosion that will generate lots of water, and this water generates some more thawing. So it's kind of a positive feedback loop here that will be generated by this process, which can evolve super fast in a couple of weeks, even days sometimes. This kind of thermal erosion gully can be formed, so super fast. And so now we're gonna travel to eastern Siberia near Yakutsk. I will show you actual results. So we are in central Yakutia. I don't know if you see my screen or the background in my office. The flag that is just behind me is the flag of the Republic of Yakutia, or Sakha, which is labeled in red here. It's a huge territory of 2 million square kilometers. We are in the basin of the Lena River, one of the largest rivers in the world, actually in between the top 5 of the Arctic basin. And the city of Yakutsk it's a pretty large city with extreme temperatures, amplitude. So during the summertime, it can go up to 30-35 degrees Celsius in July, but in December and January, it can go up down to minus 60 something. So you have an annual amplitude of nearly 100 degrees there, supercontinental climate. And so that explains why you can have both the boreal forests and super thick permafrost there. For example, here you have the map on the top right corner showing the distribution of permafrost. As I said earlier, it can be ice-rich. It is an old permafrost that has several tens of thousands of years old, several hundreds of meters thick. And one specificity for Central Yakutia there is that you have ancient thaw features that the local people call the Alas Depression here. So these are actual ancient lakes that were larger and deeper, that formed like 8,000 years ago at the early Holocene warming event. And on top of that, and these lakes are more smaller now, like shallow residual lakes that are isolated at the bottom of these depressions called Alas. And on top of that, or beside that, I should say, you have more recent permafrost thawing that we call thermokarst. And so these are lakes that are have been forming since the last few years, few decades. So these are more recent features. You have both types of lakes on the landscape. So here again is the short video mentioning how it looks like on the field. So you see this never-ending boreal forest there, a village, and different types of lakes. So right in front here, if you see my mouse here, this is an ancient lake called Alas. You have a village here, and here and there on the landscape, you can see small lakes, for example, here and here. This small guy here is a recent lake that was formed by the thawing of ice-rich permafrost recently. So the key here is that the vegetation during summertime, if you remember, this weather can be pretty warm, actually, it can go to 30 degrees Celsius. So as long as the vegetation is there, it kind of acts as a protective layer. And when you remove the vegetation, for example, for agriculture field, like here, constructions of roads or forest fires, it will, and you remove that protective layer with no more vegetation, the warm wave from the summer can penetrate in the ground and generate or start this ice-rich ground thawing. And so you have an example here, a drone image showing the lake I was just mentioning, on the previous slide, this lake here, and it forms by the melting of ground ice. This ice is like these vertical ice layers that form beneath or around those what we call the ice wedge polygons. So these are typical features of the tundra usually, but here you can have lots of them in the boreal forest. So this indicates that you have an ice-rich ground there, and the lake will develop in the next years or decades in a southeastern direction, because you see here the ground settlement that we can see when we study geomorphology there. And so we went there. We were lucky enough to go on the field 4 times just before the pandemic, and from fall 2018 to summer 2019. So once every season. And the goal was to sample a series of lakes and study them for their limnological properties. You see some examples here, and sample the dissolved gases that were in the water column there. And so here is how it looks like, the different types of lakes. And I will draw your attention on the color code here because it will be useful for later. So we have basically 3 types of lakes there. So in blue, you have those old Alas depressions that I was talking about earlier. So these are lakes that are usually shallow, and they are disconnected. They are not connected to the regional drainage basin. So they are more isolated. So their water balance will be affected by evaporation and precipitation, of course. And then in purple, you have those younger Alas depressions. We are not actually super sure about their age, but they are what they haven't specifically is that they are larger, they are deeper, and they are connected to this river that you can see here flowing from one side to the other side of the picture. So in purple, connected lakes, let's call them connected lakes. And then in red, you have these more recent thermokarst lakes that are developing with permafrost thawing that is happening right now, currently, okay? So very dynamic lakes, super different from the other guys I was mentioning earlier. So here are some results. So the top graphs are results for CO2, and the middle graphs, I will talk about them later, are actually methane. And from left to right, you have fall 2018, winter 2019, spring, and summer 2019. So for every color, you have every type of lakes. And what is super interesting here is that some lakes, like these recent thermokarst lakes, will act as source of CO2. I didn't mention that, but the graphs here, look at the scales there. The scales are a bit different, and the units means it's a saturation level compared to the atmosphere, meaning that a positive value will mean that the lake water is super saturated or oversaturated in CO2 compared to the atmosphere, and a negative value will mean that the water is undersaturated in CO2 compared to the atmosphere. So positive values acting as a source and negative values acting as a sink. And so we see that most of the red lakes, the recent thermokarst lakes, act as source of CO2, but these older last lakes in blue, when you look at the fall, spring, and summer data, they actually act as CO2 sinks. They actually pump the CO2 from the atmosphere. And so that was quite unexpected when we first received those results. And when you look at the results for methane, this is a different picture because pretty much all the lakes will act as significant sources of methane, but the concentration values, if you have a look here, if you compare fall to winter time, for example, you can have huge variations, 1 or 2 orders of magnitude, depending on the seasons here. And so why is that? We also realized that the winter conditions, also summer conditions, but here you have an example of winter conditions that will show a water stratification, meaning that if you look at the blue curves that show dissolved oxygen from the surface to the bottom, and if you also look the temperature curves in red, actually during winter time near the ice cover, the water temperature is close to 0, but the dissolved oxygen is 40-ish%. And when you go to the bottom of these lakes, the waters will be a little warmer near the 4 degrees Celsius, but specifically they will be depleted in oxygen. So this hypoxia or anoxia is good conditions to generate methanogenesis, so to generate those greenhouse gases. So in short, in summary, there was a remarkable variability in greenhouse gas emissions or concentrations between lake types for a given season, or even between seasons for a given lake type. And winter and summer conditions are really important here. There's a seasonal dynamics that we could observe because we went there several times a year. This thing, we wouldn't have been able to observe that if we went there, if we had gone there just for once. And so seasonal variations matter. And there's also, as I said, a spatial heterogeneity because ancient lakes will behave differently from recent lakes. So this is quite a challenge if you want to scale the observations or try to model these things on a bigger scale. We're not there yet, but this is something that we'll have to study in the next couple of years. And finally, here are a few slides about one of these lakes near Yakutsk, for which we could have a record, an archive of the last several thousands of years. It's close to the city of Yakutsk that you can see here on the right. And this lake here, this is a small lake called Malaya Shabida. And we were lucky enough to have a collaboration with the German team from the Alfred Wegener Institute in Potsdam, near Berlin. And they are managing a project sampling lots of lakes in eastern and central Siberia, including Central Yakutia. You can see Yakutsk here. And they are sampling lots of lakes, trying to reconstruct their history and the human activity impacts on the lake quality, for example, lake water quality. And so a couple of years ago, they were able to retrieve a nearly 7-meter long sediment core from this lake. And we were lucky enough to include this long core to our analysis. So here we have the results from the Malaya Shabida long core. For those who are not familiar with this kind of graph, from left to right, so on the left here you have a sketch of the actual core from the surface to 6.7 meter deep here, and different types of sediment that you can see here. On the left here, you have what we call the depth age model based on radiocarbon dating. So you have the age here, modern to nearly 14,000 years old to the bottom of the core. And then this central graph will show the total organic carbon concentration in percent. And on the extreme right part of the slide, you have the organic carbon accumulation rate, which is based on the sedimentation rate, which was derived from the age model, and also from the organic carbon. So it's kind of an integration between the actual sedimentation rate and within the lake, how fast the sediments are deposited, and also how rich in organic carbon the sediments are. And we basically split this core in 3 sedimentary units. One lower unit near the bottom between, so that represents from 14,000 years ago to 12-ish, 12.3 a millennia ago. So it's a unit 1. It's less rich in organic carbon. It's also a low accumulation rate. And then on the, sorry, is it showing? Yeah. In the middle, unit 2, you have organic carbon values that are really high, and you have also organic carbon accumulation rates that are really high as well. So this is the organic rich and high sedimentation unit. Sorry. And then on top, unit 3, you have still organic rich sediments, but the sedimentation rate is a little slower here. So you will have medium carbon accumulation. So that was also pretty interesting because we could document a change in carbon accumulation in one particular lake in Siberia. And just to give a little perspective here, you have a figure that I copied from a recently published paper here, showing the actual rates of organic carbon in different types of lakes. So the units, you can see it's in gram per square meter per year here, and you can see different examples across the northern hemisphere. And we see with Lake Malaya Shabida that we are on pretty high accumulation rates compared to the modern values or compared to lakes across the northern hemisphere. And so in short, if I summarize here, we have a 14,000 year long continuous, or what we think is continuous, record of carbon accumulation in the lake system, spanning the whole Holocene, so the last 10,000 years, and even the late Pleistocene, so up until 14,000 years ago. It's a precious climate or paleoclimate archive. And we could document 3 distinct sedimentary units that will document different climate conditions, from pretty cold to very warm to more stable climate. And so that will have an impact on organic carbon accumulation rates that are really high among the reported values. So this lake actually might have acted as a carbon sink in the past, which is kind of also interesting for this particular site. And so take-home messages from this talk, what I hope that you will remember is that permafrost is the less talked about or the hidden part of the global cryosphere, the world of ice. We hear about glaciers, sea ice, ice caps, that's normal. These are really the obvious candidates, but permafrost is also part of this global cryosphere. It's really important. And with climate change that is accelerating in the high latitude in the Arctic, it's thawing, not everywhere at the same speed, but still it is thawing at the global scale. And lakes in Siberia can act as both carbon sources, but also carbon sinks, as we saw either today or in the past. So really a quick note, if you want to know more about permafrost in a casual and fun way, just go to this address here, frozengroundcartoon.com. It's a project of scientific outreach with the use of comic strips or cartoons, but now we have different byproducts, and soon there's going to be even some virtual reality project about permafrost. Sorry. So I just want to thank very much the Russian colleagues, the Yakut Sakha colleagues that we worked with on the field, and even scientifically with writing our papers. These guys are has been really helpful on the field. And I also mentioned that the results I was just showing earlier are part of the thesis of the students, PhD student that I'm supervising. She's been super effective on the field and in writing papers. So cheers, big cheers to Lara, and I thank you very much.
Okay, thank you very much. That was excellent. A nice tour around the Arctic Circle and about permafrost thawing. I'm sure there are many questions. We have one already in the question and answer tool. You can also raise your hand or actually write something into the chat if you would like to have a question. Can you read the question and answers, or should I read it? I'll actually read the question and then
okay.
So Collins Gamili Hoduli asks, please, what is the shiny nature of the permafrost? Is that related to any chemical composition? And if such constituents play any role on the biodiversity of the areas they occur?
Okay, I guess that the shiny here was a mention of it's probably related to one of the pictures that I showed earlier, the ice wedges or the massive ice that we can see in the ground. Actually, it's just the shiny nature of the ice is really related to summer thawing. So you have water, a thin film of water that is just kind of dripping there. But it's not really related to any specific chemical in the ice. It's more or less massive ice. The ice, it appears a little brownish because it contains a couple of really fine sand or silt or even clay in the ice. but it's more or less just ice there. And so, yes, you have different chemical composition in the soil. So in the soil, it might be different. In the soil, you can have organic carbon, you can have inorganic carbon, you will have nitrogen and all, and a series of sulfates or dissolve and particular matter. And yes, that will make an impact on the type of bacteria or microbes that you will have in the soil when it thaws. So yes, that will make an impact on the biodiversity, but in microbiodiversity, this is far from my expertise. I mean, we work with microbiologists because people like me, I'm a geologist, so I don't understand quite much about the biodiversity, but sure, the assemblages of microbes, archaea, bacteria will be different from a given lake to another, and that will impact the type of gas that, for example, will that be more methane, more CO2, what happens with the photosynthesis. So yes, that will have an impact, but it's super complex, and we will need to have a presentation from microbio geeks here.
Okay, perfect. So then Alain Leger posted a question in the question and answer tool, but he also raised his hand. So I'll unmute you, Alain, and you can maybe ask your question yourself if that works.
Yes, do you understand me?
Yes.
Yep.
Okay. The obvious question, the question that everybody is thinking of is, what is the future regarding to the methane output? We have been told that it could be very dangerous because a lot of additional greenhouse gas, but what can you say about that?
Yeah, well, good question. I don't have a crystal ball here, but the one thing to consider about methane emissions, you will have methane bubbles if the ground is rich in organic matter. If you have a mineral soil, for example, just clay or just sand or rock, well, if this permafrost is just rock or organic poor material, when it thaws, it can be rich in ice, but if you don't have organic matter to feed the microbes, you won't generate as much greenhouse gas as we could think about. So usually when we see like, okay, permafrost will thaw everywhere and this is a climatic time bomb, actually that is not happening. You have thawing of ice-rich permafrost here and there, and the methane or CO2 will not be generated everywhere with the same speed or the same amount, because to generate methane, you need food. The microbes need food, and the food is the organic carbon. So if you have an organic rich soil, yes, that can trigger greenhouse gas production, including methane. But in some other parts of the world, for example, in Greenland, you have regions that are super mineral, like rock and clay, and you have less organic matter. So these regions will be less important for methane emissions. But for example, in peatlands in Western Siberia, yes, you can have more emissions. And again, what I wanted to emphasize during my talk is that it can vary from the summer to the winter time and different seasons. And so you cannot say that, okay, we know exactly the concentration of methane at a given year in a given region. For now, it's from what we could observe based on our field data, it's super different from a lake type to another. And so, yes, there will be regions with high emissions of methane, and there will be regions with, for example, CO2 sinks that will suck the carbon from the atmosphere. So the global picture for now is more complex than we usually read about.
Okay, excellent. Thanks a lot.
No risk of runout. There is no obvious risk of runout emission of the methane itself, not the one which is going to be product, but the one which is already kept in the soil.
Yeah, you mean some methane that will be already in the soil? Is that something?
Yes.
Yeah. Well, I guess in some peatlands, you don't. I'm not a specialist, but you don't need to have frozen peatlands to have. You don't need permafrost to have methane emissions in peatlands because you have hypoxic or anoxic conditions there. So you already have some methane generated there. But the methane is, I don't know, its resonance time in the atmosphere is much shorter than the CO2. So in a few years or a decade, your methane there will be spread in another compartment of the global system. So maybe I don't understand the question that much, but this is a different type of mechanism, and it's not specific to permafrost regions, I would say.
Yeah, I think there are also gas hydrates at the seafloor, which we are also afraid of, that they solve, which also contain methane, and then that will also contribute to global warming.
This is another, you also have methane hydrates that are stuck at the bottom of the seas in coastal regions, and this can trigger sometimes degassing events. And you also have some permafrost underneath these water systems. But again, I'm not a specialist of that, but this is something that they are monitoring right now.
Mm-hmm. Okay, I hope that answers your questions, Alain.
Okay, yes.
Is that?
It's perfect. Okay, then we have a question by Isolde van Riemsdijk asking about the debate if we should worry about the changes or if that actually happened before and that this is how it is, so to say.
Yeah, well, one example I showed was those Alas depressions. So those very old, depressions that are dating from 7,000–8,000 years ago, and this happened in an event or a period of climate warming that has been documented in the whole Siberian region. And the estimations are that nearly 40% of the total Yakutian territory has been affected by thermal karst, so ice-rich permafrost thawing, in the early Holocene, like 8,000 years ago. So that's a huge territory. And of course, we can imagine that some methane and CO2 was released back then, 8,000 years ago. And so this is one thing. This is one climate change that happened in the past. But the difference compared to today, I would say, is the speed at which this happened. The warming events of the early Holocene probably happened on the century or millennium scale level for several thousands of years. And now the lake evolution, now the permafrost thawing now is happening at the speed of decades or even some individual years. So I guess the debate about climate change is one thing to consider is the speed at which this is happening right now. It's faster than it used to be.
Mm-hmm. Okay, thank you very much. I maybe have a small detailed question about the Alas. In the images you showed, one sees that around the lakes there is a lot of free space where no trees are growing. Why is that? Why is the area not recovered by trees?
Yeah, that's a good question. So the Alas are topographic depressions, and they are there since a while. And the people, the Sakha people, have been using these historically, traditionally for they are a horse or a reindeer herders, and they have been using these spaces as pasture. Is that the right word? So they have been using the depression as pastures for the animals, and sometimes they would construct their farms in the Alas. So the Alas is also, I mean, it's interesting for a geologist like myself studying permafrost, but it's also it's first and most, it's a traditional feature of the landscape, and it's important for Yakut people. So pastures, that's why you don't have growing trees there. They have been using this to grow for their animals.
Mhm.
And you also have different type of soil now, because you have ancient soil that used to be rich in ice, and that is now thawed. And so you have different types of soil at the bottom of the depression. So I guess for biogeochemical cycles, it's a bit different there as well, because you don't have any more ground ice at the bottom of these depressions.
Mhm. Okay. Alessandro Forte raised his hand. Please, Alessandro.
Yes, thank you. I don't know if you can hear me.
Yes.
Also, I want to thank you for this talk, Frédéric. It's really interesting and covers some obviously critical questions, very pressing questions. And my question goes back to an earlier part of your talk where you were showing us an image of the active layer.
Yeah.
Now, this is presumably getting deeper, actually, over the last few decades. Is that something you're documenting as well?
Yes, in different, and not only in Siberia, in different parts of the world, there are proofs or clues that the active layer has been thickening more or less quickly over the last decades. So it means that it will change some surface hydrology, of course. It will also, and in some regions, maybe not in the northernmost part, but for example, in the discontinuous zone of the permafrost, it can mean that some years during the winter, it's not cold enough to freeze back all the active layer on its whole thickness, meaning that you can develop some unfrozen layers between what's left of permafrost beneath and the frozen ground, the winter frozen ground on top. So sometimes it will start to generate some unfrozen layers. We call these layers thallics, and that can impact the hydrology and biogeochemistry as well. In Eastern Yakutia, for now, it's so cold during the winter time that even with a active layer of 2 meters, it's pretty thick during the summertime. The ground thaws until 2.2 meters deep, and it freezes. It's so cold during the winter time that it will freeze back entirely for next winter, because it's -65. But in some other parts of the Arctic or boreal regions, if it continues to thicken, yes, you will have some unfrozen layers in the upper part of the permafrost.
The second part of my question was regarding the active layer. Is there a quantitative, or can we quantify the relationship between the depth of the active layer and the horizontal scale of these slumps and the craters, the thaw craters that you see?
Good questions. I don't know. The craters I was mentioning, these guys, these features are, from what I could understand, this is pretty new, but a couple of papers were mentioning that they are formed by the thawing of what we call pingos, like the really steep sided permafrost mounds, like cones. Yeah, those mounds that are super abundant in Western Canada and in Siberia as well. So pingos, when they start to thaw, the dissolved gases that are stuck just underneath will get into high pressure, and that will generate a kind of, not a violent explosion we could see, but like a collapse of the metal part, and the dissolved gases will escape. And so the actual size of the crater will be directly influenced by the size of the pingo. And usually the pingos will make a couple of tens or hundreds of meters diameter. So this fur crater is more, I would say, more or less a few tens or hundreds of meters wide in diameter. For thaw slumps, it might be different. It will depend on the ground ice, the ground ice content that you have in your soil, and the extreme. That, I mean, the biggest from far, the monster of the thaw slumps is the they call gateways to hell. It's in Batagay. So if you search for Batagay, it's in northern Yakutia. And it's something like almost 1 kilometer wide by 100 of meter high. The cliff of this thaw slump is really huge, and it was started. It started in the 1950s or 60s, I think. It's human activity, anthropic triggered, but now it has been evolving with ongoing climate. And the thing is that the permafrost there is super old, and it was formed when the climate was colder. Now it's not in equilibrium with modern climate. If some summer warm heat goes into the ground right now, because, for example, you remove the vegetation, that will generate some thawing. The climate is warmer today than it was like 20 or 40,000 years ago. And so, yes, there are some impacts, but again, the size of the thaw slump will depend on the local geomorphology, the slopes, the topography, and also the ground ice content.
Thank you. Very nice talk. Thanks.
Thank you.
Okay. I think it's 5 o'clock. Are there any urgent questions? Otherwise, would you mind to repeat the link or this hint to your frozen grounds outreach?
Yeah, it's one word, frozen ground cartoon with no S, because at the beginning it was just one cartoon. Now it's several cartoons, but anyways, frozen ground cartoon in one word.com. That's super simple.